Autophagy, the process by which cells recycle their own damaged components, is essential for cellular maintenance, repair, and longevity. As we age, this critical cleanup process tends to slow down, contributing to the accumulation of dysfunctional organelles, protein aggregates, and oxidative stress. Increasingly, research is shedding light on how not just macronutrient signals, but specific vitamins and the enzymes they activate are vital for maintaining autophagic activity. Among these, vitamins B2, riboflavin, B3, niacin, and B6, pyridoxine, play especially important roles by serving as indispensable cofactors for key enzymes that regulate cellular energy status, oxidative defense, and repair, all of which intersect with the machinery of autophagy. Vitamin-dependent enzymes are not mere background players. They often serve as gatekeepers for energy balance and redox control, two of the primary cellular cues for initiating autophagy. Autophagy is turned on when cells sense a drop in energy availability or an increase in oxidative damage, and these signals are transduced through enzymatic systems that rely directly on B vitamins for their function. Riboflavin, B2, is required for the synthesis of flavin adenine dinucleotide, F80, and flavin mononucleotide, FMN, both of which are critical cofactors for a variety of redox enzymes, especially those in the mitochondrial electron transport chain. Complex 2, succinate dehydrogenase, for instance, is an FAD-dependent enzyme that connects the citric acid cycle to oxidative phosphorylation. When riboflavin levels are insufficient, mitochondrial respiration becomes inefficient, leading to increased oxidative stress and impaired ADP production, two key triggers for autophagy. By supporting energy production and managing ROS levels, riboflavin indirectly sustains the metabolic conditions necessary for balanced autophagy. Niacin, B3, stands out as one of the most directly impactful vitamins in autophagy regulation due to its central role in NAD metabolism. NAD is the essential cofactor for sirtuins, a family of deacetylase enzymes that regulate gene expression, mitochondrial biogenesis, and autophagy. SIRD1, in particular, activates autophagy by deacetylating several autophagy-related proteins, including ATG5, ATG7, and LC3, and also interacts with the FOXO family of transcription factors to promote oxidative stress resistance and DNA repair. Low NAD levels, which naturally occur with aging, can inhibit sirtuin activity, dampen autophagic responses, and accelerate cellular dysfunction. By increasing NAD availability, either through diet, supplementation with niacin or its derivatives like NMN or NR, or through fasting, sirtuin-dependent autophagy pathways can be reactivated, helping cells maintain resilience. Vitamin B6, pyridoxine, is essential for amino acid metabolism and neurotransmitter synthesis, but its relevance to autophagy lies in its role as a coenzyme for enzymes involved in transamination and glutathione synthesis. One of the key challenges cells face during aging is managing oxidative stress, and the glutathione system is a major line of defense. B6 is required for the activity of enzymes like glutamate cysteine ligase, which initiates glutathione biosynthesis. Maintaining sufficient glutathione helps neutralize ROS, which in turn prevents excessive oxidative damage that could overwhelm or dysregulate the autophagy process. Furthermore, B6 participates in the production of sphingolipids and other signaling molecules that can modulate lysosomal function, the final step of autophagy where waste is broken down and recycled. Together, these three vitamins act like tuning dials on the cell's ability to respond to stress and initiate repair. Their dependent enzymes form a network that maintains the mitochondria in working order, keeps energy and redox balance in check, and facilitates the turnover of damaged components through autophagy. When the availability of these vitamins declines, as often happens with age, medication use, or poor diet, so too does the efficiency of autophagic machinery. This leads to a feed-forward cycle of increased cellular waste, declining metabolic function, and accelerated aging. Moreover, vitamin-dependent enzymes operate in concert with nutrient-sensing pathways like AMPK and mTOR. YMPK, which is activated during energy stress, promotes autophagy and is itself supported by NAD and upstream enzymes that require B vitamins. mTOR, the major inhibitor of autophagy, is suppressed under conditions of low nutrient availability or high cellular stress, states that are better tolerated when B2, B3, and B6 are abundant and cellular energy metabolism is intact. In other words, The vitamins don't just support enzymes passively, they actively shape the cell's capacity to respond to metabolic cues and repair itself appropriately. What makes this model especially promising for anti-aging strategies is its accessibility and low risk. Unlike pharmaceutical interventions that target mTOR or autophagy directly, often with side effects, ensuring optimal intake of riboflavin, niacin, and pyridoxine offers a foundational and sustainable approach. These nutrients are generally safe even at higher intakes, within reason, and can be delivered through a combination of food sources, like organ meats, eggs, legumes, and leafy greens, and targeted supplements. In older adults or individuals under chronic stress, supplementing with active forms, such as riboflavin, 5-phosphate, nicotinamide riboside, or pyridoxal, 5-phosphate, may be especially effective at restoring enzymatic activity. In conclusion, the interplay between vitamin-dependent enzymes and autophagy pathways is not just a biochemical detail, it is a critical determinant of how well cells maintain themselves over time. By supporting the enzymes that govern mitochondrial efficiency, redox balance, and adaptive gene expression, B2, B3, and B6 help ensure that autophagy occurs at the right intensity and frequency to keep cells youthful and functional. Optimizing these vitamins offers a compelling, low-intervention way to reinforce the body's natural longevity mechanisms, providing the biochemical tools cells need to clean house, repair damage, and age more gracefully.